A few years ago, an audience member pointed out that I always seem a little too happy when discussing death and destruction from the sky. I'm not actually excited about our universe trying to kill off humanity. I'm excited about science. And it just turns out that a lot of science involves the universe trying to murder us in myriad different ways. In today's episode, we're going to look at everything from how past Earth couldn't support photosynthesis because the days were just too short, to current Earth letting us get hit by more cosmic rays prior to earthquakes going off, and to supernova threatening our world while alien stars eat other planets. Science, sometimes, is just kind of violent. And if I seem excited, well, I like science, even if science doesn't like us. If you were watching this before July 14th, you actually have the opportunity to see just how much I and our whole team at EVSN and CosmoQuest all love science. On July 15-16, we're going to be hosting a 36-hour hangoutathon over on twitch.tv/CosmoQuestX. During this old school fundraiser, we're going to be talking about science and battling it out in a moon-based building competition that pits Lego builders against Minecraft diggers. We invite all of you to join in the shenanigans and help us raise money for science and science communications. Learn more at cosmoquest.org. As a reminder, this show is produced thanks to the generous contributions of people like you and is released under Creative Commons. Watch, share, and if you can, donate to keep us going into the future. This is Escape Velocity Space News. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. As we gear up for our yearly fundraiser, I feel confident in saying that just about everyone on our team is wishing we could somehow cram more hours into every day. At a certain level, our world is happy to oblige, and every year our days get the smallest fraction of a second longer, and the moon gets a few centimeters farther away. In science, we often find things related in the wildest of ways. In this case, conservation of momentum is trying to keep everything rotating with the same total momentum. We have the Earth rotating about its axis, the moon rotating and revolving around the Earth, and the Earth and moon going round and round the sun. All things being constant, everything would stay exactly the same forever, but things aren't exactly constant. Because our Earth isn't perfectly spherical, the moon's gravity is pulling on mountains and other high mass points a little bit harder, and in the process slowing our world's rotation. As the Earth slows, the moon moves outward. This is the same physics that describes how an ice skater can slow down by flinging their arms outwards. In this simple situation, every day from here forward will get a little bit longer, and every day, looking back through history, we thought the days would be a little bit shorter. But the universe and our planet are rarely simple, and it turns out that our moon isn't the only thing affecting our world. Our sun also affects the Earth, and it has the ability to speed things up. And new research shows that when the Earth's day is about 19 hours long, the moon's habit of lengthening the day and the sun's efforts to shorten the day almost balance out. According to a new paper by Ross N. Mitchell and Hugh Kirschner appearing in Nature Geoscience, Fossil records indicate that from about 1 billion years ago to about 2 billion years ago, our Earth's rotation rate stalled out at about 19 hours per day. During this time, evolution also stalled out in its own way. Photosynthetic bacteria weren't able to create the oxygen rich atmosphere we enjoy until the days grew longer. This means life as we know it actually requires a longer day. As we go looking for life elsewhere among the stars, it looks like there will be a sweet spot where a world rotates fast enough to maintain even heating and decent weather, and slow enough to maintain photosynthesis. Lots of different things can affect the Earth's rotation. Our world really is a really big version of a spinning ice skater, and just as every tilt of the head and movement of the hand will change the ice skater's rotation, every change in the distribution of land and sea can change the Earth's rotation. We hear about these changes on the news when big things happen, like the filling of the Three Gorges Dam in China, which slowed our planet by 0.6 seconds per year. What we sometimes miss is how small things can build up to also change things. In a new paper in Geophysical Research Letters, researchers led by Qiwan Xiao document how the pumping of groundwater changed our planet's rotation and tilt. It's estimated that 2,150 billion tons of groundwater was pumped out of the landscape between 1993 and 2010. This is enough water to raise sea levels by 6 millimeters, or about a quarter of an inch. This redistribution of mass has moved the Earth's rotation axis about 80 centimeters and will continue to change our planet as we continue to pump water, use it in our homes and businesses, and send it back into the environment. According to Xiao, quote, observing changes in Earth's rotational pole is useful for understanding continent-scale water storage variations. Polar motion data are available from as early as the late 19th century, so we can potentially use those data to understand continental water storage variations during the last 100 years. Were there hydrological regime changes resulting from the warming climate? Polar motion could hold the answer. End quote. This kind of research really shows how everything is connected, from household water pumps to the sun's push and pull on the Earth. Everything plays a role in our planet's evolution. And sometimes this interconnectedness can lead to the weirdest relationships. In the pursuit of a way to predict future earthquakes, researchers realized that cosmic ray detectors received more particles in the weeks leading up to earthquakes than at other times. As research lead Piotr Homala says, quote, at first glance, the idea that there is a link between earthquakes and cosmic radiation in its primary form reaching us mainly from the sun and deep space may seem strange. However, its physical foundations are fully rational. End quote. Those rational explanations? Our Earth's magnetic field is generated deep within our world, and normally that field does a smash-up job blocking cosmic rays. But if something interferes with generating that magnetic field, more cosmic rays will reach our world. This seems to indicate that an upcoming earthquake affects circulation inside our planet prior to triggering a shift at the surface of our planet. Currently, we can see changes in cosmic ray counts about 15 days prior to a quake. This is good. What we can't do is say where on the planet the quake or quakes will occur, which is bad. But this is a start. This research, published in the Journal of Atmospheric and Solar Terrestrial Physics, is the first solid evidence that earthquakes do warn us they are coming. The details? That's future research. After a short break, we're going to leave our world behind and take a look at stars behaving badly. Stay tuned. One of the weirder puzzles of astronomy is the presence of large planets snuggled up next to their stars. In young solar systems, we can at least say the star likely migrated there and isn't destined to live very long. But the system 8 Ursa Minor is an elderly star with a large planet on an orbit a lot like Mercury's. And this particular combination just isn't expected. As stars evolve, they can change in radius as the cores burn hotter or cooler. Someday, our own sun will blow it up and likely consume Mercury and Venus and possibly even Earth. Much later, it will collapse down to an object just the size of the moon, and we'd expect to see an empty swath of space surrounding it. 8 Ursa Minor appears to be burning helium in its core, which means it should have gone through a red giant phase in the past and emptied out its surroundings. The existence of a planet says something weird has to be going on. In a new paper in the journal Nature, researchers led by Mark Hyun offer up 3 different possibilities. On one hand, it may just be that this planet managed to survive being engulfed by a star. While this seems insane, it's not impossible. The outer layers of a star just aren't that dense, and it's possible the planet got moved around but not destroyed when the star engulfed it. It's also possible that instead of seeing a star that used to be a red giant, we're seeing a star that used to be 2 stars. A merger could have prevented the resulting object from ever ballooning up into a red giant while explaining the helium burning we see. It's also possible that while the star is old, the planet is young and somehow formed in the star system's old age as part of a second generation of planet formation. However this planet got there, we now know solar systems come in even more diverse designs than we'd previously dreamed. I now want someone to write a book about some society future-proofing their civilization to survive inside their bloated out sun for millions of years. Any authors out there? Can you make this happen? Most planets just aren't this lucky. Instead, we're now realizing that some of the flares we see coming from young stars may actually be stars eating their planets. About 85 years ago, the young star Fu Ori increased in brightness. In general, brightness variations in young stars aren't unusual. But the enduring nature of this particular flare and similar flares seen in other stars has caught researchers' attention. In a new paper in the monthly notices of the Royal Astronomical Society, researchers led by Sergei Nakashin model just how this kind of a situation can take place. Young stars like Fu Ori sit inside a large disk of infalling material that is both feeding into the star and providing material for planets to form. Inside this disk, the seeds of massive planets can create massive knots. The lucky knots of material clear out a stable orbit a healthy distance from their star and eventually form planets. In Fu Ori-like stars, these knots don't stay put. Instead, they rapidly migrate starward until they are just 10% of Earth's distance from the sun. This close to their star, these would-be planets are superheated until they ignite. As Nakashin describes, quote, "We discovered a new process which you might call a disk inferno of young planets." End quote. This discovery has some rather destructive implications for young solar systems. Nakashin goes on to explain, quote, "Protoplanetary disks are often called nurseries of planets, but we now find that these nurseries are not quiet places that early solar system researchers imagined them to be. They are instead tremendously violent and chaotic places where many, perhaps even most, young planets get burned and literally eaten by their stars." End quote. To be entirely honest, Stars can find lots of different ways to destroy planets, and they don't always limit themselves to destroying their own planets. In star forming regions, the largest stars form first, and those largest stars may go supernova before the smallest stars even finish forming. In looking at meteorites from our solar system, researchers find the atomic fingerprints of a supernova going off just as our system was forming, and leaving in its wake a variety of radioactive elements that otherwise would no longer exist. Under normal circumstances, this kind of a nearby blast should have blasted apart our solar system and prevented our world and others from even forming. But since we are here and the supernova's remnants are here, something must have happened to dampen the supernova's impact. But what? It turns out the answer was in the stars. In studying current star forming regions, researchers note that cold filaments of material stretch throughout these systems, hiding active star formation. Just as these filaments can make it hard for us to see baby stars and their worlds, these filaments may also serve as a blast shield that protects them from the larger siblings supernova. In a new paper in Astrophysical Journal Letters, researchers describe computer models that show it would take at least 300,000 years for the blast wave to break up the dense filament around our forming solar system. The components of meteorites enriched in radioactive isotopes formed in approximately the first 100,000 years of our solar system's formation inside a dense filament. This research, led by Doris Ajamanen, shows that we can better understand our own solar system by studying other systems like our own. We can't see pictures of our own solar system's early years, but we can see other solar systems that are now going through what we went through. Science, it has stayed the same, and it makes this kind of an understanding possible. Supernovae are one of the primary ways our universe spreads around heavy elements. From the first stars came the first supernovae, and with them came the first elements capable of building planets and life. And supernovae don't only come from massive stars exploding. We can also find supernovae in elder star systems where the relics of stars like our sun can be detonated like so much TNT. Earlier in the episode, I mentioned that one day our sun will collapse down to an object the size of the moon. Essentially, after our star bloats up into a red giant and after it has run out of fuel to power its nuclear reactions, it will exhale its outer atmosphere and the remaining core will collapse down into a glowing ball of very hot gas. That remnant cinder is called a white dwarf star, and they always have a mass less than 1.4 solar masses. If their mass is to somehow get larger, they will become unstable and explode. In general, a random white dwarf is in no jeopardy. But when a white dwarf forms with or ends up with a companion star, mass can get transferred, and a white dwarf can find itself growing up to that 1.4 solar mass maximum and exploding. Since these stars all have about the same mass when they detonate, they all give off about the same amount of light, and we can use them to measure distances through space. Numerous telescope surveys and systems are dedicated to finding supernovae, including the Zwicky Transient Facility at Palomar Observatory. In 2022, that particular survey spotted an unusual supernova taking place. In the low-resolution images from Palomar, all the researchers saw was an overly bright blob of a galaxy. In higher resolution images from Keck, researchers saw 4 pinpricks of light. With careful modeling, researchers realized they were seeing a nearer galaxy, just 2.5 billion light years away, bending and magnifying the light of a supernova 4 billion light years away. The light was enhanced at least 25 times, allowing researchers to see an event that could otherwise not have been seen. This research was described in Nature Astronomy and was led by Ariel Gubar. Remarkably, this chance alignment didn't just magnify one image of the supernova. The most perfect of alignments will create a gravitationally lensed circle of light, and a not quite perfect alignment will create a cross. In this case, the researchers saw a cross, but only briefly. Supernovae rise rapidly in brightness and then fade away as their explosions expand and cool. In time, this brilliant interplay of light and gravity will fade away. We are used to studying our universe in light. But the truth is, we're also able to study our universe by looking at particles like cosmic rays and neutrinos, and by looking for gravitational waves. In this week's Closer Look, we're going to look at what scientists are starting to learn from this multi-messenger astronomy. Stay tuned. Heading into the holiday weekend, social media exploded with news that a massive discovery was going to be announced on Thursday, June 29th by the NanoGrav collaboration. This network of North American observatories had been watching the sky in radiolight for 15 years, and now they had something big to share. For those who'd been following the team's work, hopes were high. This team had been carefully monitoring the metronome-like ticking of radio pulsars to see if they could see alterations in the fabric of space-time that are caused by gravitational waves. That big news, we hoped, would be a description of our universe warping in observable ways. Funded by the National Science Foundation in 2015, NanoGrav used the Arecibo and Green Bank radio dishes, as well as the CHIME and Very Large Array, to monitor an ever-increasing number of pulsars. These spinning neutron stars blast out radio light like an over-caffeinated lighthouse spinning 1,000 times a second. Neutron stars are the high-density remnants of massive stars. Like the white dwarfs we discussed earlier, they are left over after a star can no longer fuel its nuclear reactions. While a white dwarf is made of high-density normal matter, a mixture of electrons, protons, neutrons, the stuff that makes up our atoms, neutron stars are just what their name implies. Giant balls of just neutrons. Because these particles can get much closer together than a mix of protons and electrons, neutron stars can cram all their mass into a volume that could rest comfortably on Manhattan Island. That mass, it is 1.4 to something like 2.2 solar masses. When that much mass crams into a space that small and spins that rapidly, you end up with a nature-made top that doesn't have a single wibble or wobble to its motion. A standalone pulsar is the ultimate clock. And when we find pulsars paired up in binary systems, their orbits can be precisely measured by the shifting of their pulses. Essentially, as the pulsar moves toward us in its orbit, each pulse has to travel a little less distance than the one before, so the ticking of the clock seems to speed up. As the pulsar moves away from us, each tick has to travel a little bit farther, and the beating seems to slow down. This kind of timing measurement is so accurate that the first planet ever discovered was found in 1992, orbiting a pulsar that it ever so slightly moved to and fro in a detectable way. Their precision rotation makes pulsars true beacons in the sky, and many sci-fi series have used them as navigational plot points. The gold plate on the Voyager mission even included a map indicating where our solar system is located relative to a series of pulsars. And if our universe is made of stretchy space-time that can expand and contract as Einstein predicted, these beacons should move with the space, and that motion should show up as tiny timing variations in the pulses. According to Einstein, this kind of stretching of space can occur when massive objects combine and send gravitational waves rippling through the universe. If a lonely pulsar with no planets or stellar companions appears to move ever so slightly to and fro, we might be seeing space getting smaller and larger in response to a gravitational wave, while the pulsar actually stays put on the fabric of space-time. Measuring changes in the ticking beat of a millisecond pulsar is not exactly easy. And if researchers only see one pulsar seem to change just once, there's no way to know if the measured time is wrong or space is stretching. This is why researchers monitored as many pulsars as they could. As a wave moves through space, we should be able to see pulsars in different places get affected at different times. Pulses in line with the moving wave will appear to change in one way, while those off to the side will appear to change in a different way. The math is actually pretty straightforward compared to a lot of other stuff in astronomy. When this project was funded, ground-based gravitational wave detectors still hadn't found anything. And many folks, myself included, were starting to think that we'd never be able to detect the tiny variations in space-time affecting our planet. Systems like LIGO and Virgo are sensitive to everything from seismic noise to passing trucks. While pulsars wouldn't allow us to see the small gravitational waves that LIGO and Virgo might detect, they would let us potentially see the massive waves from merging supermassive black holes and other giant systems. So, in 2015, with funding from NSF, researchers joined together to monitor pulsars. In 2016, LIGO and Virgo did announce their first detection of the merger of two stellar mass black holes. And the folks at Nanograv just kept monitoring and kept monitoring. And we would get hints in papers and conference presentations that fluctuations were being seen, that the data was sensitive enough for the experiment to work, and that someday we'd have a new way to see our universe. And on June 23rd, in a series of papers, Nanograv released their data and said, "Look, the signal is here. We can see the fabric of space being wibbly-wobbly through the tiny, timey-wimey changes in pulsar ticks." The central result, highlighted in a special issue of the Astrophysical Journal Letters, is the correlation in timing variations measured in 68 pulsars with 3 or more years of data. Looking at 2,211 distinct pairs of events, they are able to replicate within error the expected signal of supermassive black holes merging and rippling our universe with their gravitational waves. The signal is clear, but the data is still noisy and doesn't yet allow researchers to say, this timing event is related to something that happened in that exact direction. We can't yet see a gravitational wave signal and then point a telescope to see what happened. Not yet. But now, this is just a technological problem. And it isn't a problem that only Nanograv is working to solve. Other collaborations around the world also raised their hands and said, "We saw this too." From OzGrav using Parkes Radio Telescope in Australia to the Chinese Pulsar Timing Array on FAST to myriad other teams, this result is being seen to varying levels of accuracy by researchers around the world. And with Nanograv's data release, we can look forward to seeing more teams release their data and with their combined results, get a better and better understanding of what is going on. Until one day, we can see gravitational waves and point our telescopes and say, yes, I see the source. More than 400 years ago, Galileo pointed a handmade telescope at the stars, the moon, and the known planets. When he made his observations, many saw our world as perhaps the center of a universe with just 5 planets, a moon, the sun, and a sphere of stars. There were some who granted that maybe the sun could be the center, but we really had no idea of the vastness of our universe. In 400 years, our study of the universe using light has allowed us to piece together a detailed understanding of how our universe expanded out into what we see today, how stars form, and how planets come to be. We know that we are stardust, and we know that there is a lot that we don't know because light only allows us to see so much. And all events from moment zero to 400,000 years after the universe formed are hidden behind the cosmic microwave background light. But gravitational waves, they don't have that barrier. We may one day be able to see with gravitational waves all the way back to the beginning of time. Maybe. One day. And I kind of feel like on that future day, folks will look back on 2015 and the start of nanograv, and look back on 2016 and LIGO and Virgo's first detection, and look at this detection in 2023 and say, and this is where it started. Not with one man with one handmade device like Galileo, but with massive collaborations of humans working together to push technology for one simple reason: to see what science can be seen. After our break, we'll be joined by Eric Mattis to look back on recent launches. Stay tuned. And now it's time for spacecraft news. I'm pleased to welcome on aerospace correspondent Eric Mattis for this week's Tales from the Launchpad. Hey, Eric.
Hi, Pamela. Since our last episode, there have been quite a few launches, and there was even a suborbital launch by an orbital launch company, which I'll tell you at the end. First up, back on June 15th at 0530 UTC, China launched a Long March 2D from the Haiyuan Satellite Launch Center, carrying 41 Jilin-1 satellites to orbit. Jilin-1 is China's first domestically developed commercial remote sensing satellite system. This sets a new record for most satellites on a Chinese launch vehicle. They are part of a planned 300 satellite constellation, making it the largest Chinese commercial satellite constellation. The Jilin-1 satellites come in several different sensor configurations, including high-definition video, hyperspectral, and other types of optical imaging systems. They're similar to the Gaofen military satellites, but these are for commercial users. Next up, on June 18th at 22:21 UTC, SpaceX launched a Falcon 9 from Slick 40 at Cape Canaveral Space Force Station. Aboard was an Indonesian telecommunications satellite called Satria-1, going to geosynchronous transfer orbit. According to the Jakarta Post, Satria-1 is envisioned to boost connectivity inclusion in the country, providing free internet connection to 150,000 public facilities, including schools, regional government offices, health facilities. It will have a throughput capacity of 150 gigabits per second, 3 times the capacity of the 9 telecommunication satellites that Indonesia currently uses. China launched a Long March 6 rocket from the Haiyuan Satellite Launch Center in northern China on June 19th. Xi'an 25 is a new type of Earth observation technology experiment exploring uses for land resource research, urban planning, disaster prevention, and mitigation. According to reports, the satellite was successfully deployed into the desired orbit. A couple of days later, a classified National Reconnaissance Office mission known as NRL-68 was launched from SLIX-37B at Cape Canaveral Space Force Station on June 21st at 0329 UTC, aboard a United Launch Alliance Delta IV Heavy. This was the 15th and penultimate flight of the Delta IV Heavy launch vehicle. The payload is designed, built, and operated by the NRO in support of the agency's national security mission to provide intelligence data to U.S. senior policymakers, the intelligence community, and the Department of Defense. In other words, it's a gigantic spy satellite. SpaceX launched the Euclid Dark Energy Telescope on July 1st using a Falcon 9 rocket. Euclid has a 1.2-meter telescope which will measure the redshift and distance of up to 2 billion galaxies in its 6-year mission to help unravel the mysteries of dark energy and dark matter. Led by the European Space Agency, it'll make a 3D map of the universe by observing more than a third of the sky out to over 10 billion light years. The third dimension of the map will actually be time. How the universe has evolved over the past 10 billion years will show how it has expanded and how structure has formed, which will allow astronomers to figure out the properties of dark energy, dark matter, and gravity. The telescope includes two scientific instruments, a visible wavelength camera called VIS, and a near-infrared camera spectrometer called NISP. It will take Euclid about a month to reach the Sun-Earth Lagrange point 2, L2, where it will orbit around 1.5 million kilometers from Earth. This is a popular spot for space telescopes, and among the others out there are Gaia and Webb. The final launch of the Ariane 5 rocket was on July 5th, concluding 25 years of workhorse service for Europe. VA261 was the 117th Ariane 5 launch. The mission numbers count up from the very first Ariane 1 launch back in 1979. Ariane 5 ends its career with 112 successes, 2 failures, and 3 partial failures, a very respectable record for an orbital launch vehicle. Its replacement, Ariane 6, is expected to enter service next year. This has led to a gap in launch capability for European rockets, something that SpaceX has exploited by picking up several launches of European satellites in 2022, 23, and 24 that would have used Ariane 6 had it been available. The gap was not planned, but was a result of delays from the war in Ukraine and the pandemic. Europe also lacks a medium lift rocket following sanctions imposed after the Russian invasion in Ukraine. Euclid, which we just talked about, was originally intended for a Soyuz rocket, but was moved to SpaceX with a delay of only a few months. Last but not least, there were 3 batches of Starlink satellites launched on Falcon 9 rockets. And we also had an interesting suborbital launch since the last show. It's interesting because rather than being a sounding rocket or other type of suborbital launch vehicle, this one used an Electron rocket made by Rocket Lab. Dynamo A was launched on June 17th at 2124 UTC from the Mid-Atlantic Regional Spaceport on Wallops Island in Virginia. This was the first launch for Rocket Lab's Hypersonic Accelerator Suborbital Test Electron program, or HASTE. HASTE is based on their Electron rocket with a modified third stage that offers a larger payload capacity of up to 700 kilograms. Because it's a liquid-fueled launch vehicle, they can offer custom trajectories for the passenger's hypersonic and suborbital requirements. Not much is known about the payload at this time, as it was a classified mission, but Rocket Lab confirmed the mission was successful, whatever it was. We keep track of orbital launches by launch site, also called spaceport. According to RocketLaunch.live, so far this year, USA has had 48 launches, China 22, Kazakhstan 5, India 4, New Zealand 3, French Guiana, Japan, and Russia each have had 2, and Israel, North Korea, South Korea, and the United Kingdom each have had 1. Of these 92 launches, there have been 5 failures, reminding us that space is hard. That's it for now.
Thanks, Eric. Before we go, I'd like to share one final fact. On July 9th, 1979, the Voyager 2 mission made a flyby of Jupiter. This is the first space event I can remember, and I have to admit that memory mostly consists of 5-year-old me insisting I didn't need to take a nap to stay up to see images on the TV of Jupiter. From these images, and the images taken in April of that year by Voyager 1, we learned of Jupiter's rings, Europa's ices, and Io's volcanism, and so much more. These missions and their exploration of the solar system would be celebrated a few months later in the December 1979 blockbuster, Star Trek: The Motion Picture. 10 years later, many of the young researchers who were part of Voyager got to see the launch of the Galileo mission, which in 1995 would become the first spacecraft to orbit Jupiter. Today, the Juno mission, working with some of those same people, has taken up residence in the Jupiter system, and by the end of this year, we'll have our closest ever images of Io's volcanoes. Science is a slow process, but it does advance one life of research at a time. Good night, everyone, and remember to look up.